Okay, so welcome to Math 344, the math of sports. So this is the first time I've done a class like this, not as a winter study, not as an independent study. So we have a lot of flexibility. If any of you are on any teams on campus or any clubs and you want to incorporate something from that into this class, you're always up for your choices of material. I will try to have all the information available on my homepage. Williams is migrating away from the FTP, SFTP systems I've been using for over 2 decades. So, things are a little bit in flux right now as to where will things eventually live. And so I will keep you updated, but I will always be recording the lectures. I will always be posting the slides. So if you have to miss something, not a problem. If any of you are seniors, I understand that being a senior is at least a 5th class. Far more important than a class is, preparing for interviews, going for interviews and stuff like that. Always happy to work with you on deadlines, so long as you let me know at least 24 hours in advance. Sometimes things happen out of the blue. You've just been invited to the White House to receive, a Medal of Honor. That's fine. We can work around that. But most things you should know with plenty of notice so that you can say, hey, I need an extension on this. I'm going to be out. Okay. Piece of advice from my brother: party less than the person next to you. Seeing if anybody has no neighbors. Okay, so everybody can have at least some fun this semester. Take advantage of office hours and mentoring. Once you leave college, it's not going to be as accessible in many places to have people who will, care, who will be available to you. This is why you come to a school like Williams. Unlike most professors, I do not try to get to know my students. I want you to try to get me to know you. I am happy to go for a walk, grab coffee, grab dinner. If I'm in my office, it's office hours. I want to get you to the point where you are comfortable talking to people and reaching out. At least one professor a semester, you should try to get to know well. This way, even if you're only successful half the time, you should have enough people who can not only write a letter of recommendation for you, but are aware of what are you good at, what are your interests, so that they can give you, hey, here's some opportunities that might be up your alley. Let me just pass this along. So you really try to get to know the people, because we are the ones who have only you to give opportunities to. We don't have grad students yet. We don't have postdocs. I've had a lot of students work with me on multi-million-dollar lawsuits for Major League Baseball and the like. Freshmen already know enough to be able to do stuff like this. If you don't know how to code, we're going to do at least a little bit of coding in this class. It's something that is extremely important to use. I used to say that if you knew probability statistics and could code, you could always get a job. Because someone sued their school when they didn't get a job upon graduation, I no longer say that, because I don't want to keep myself or this institution of higher education exposed. I will say I will be extremely shocked if you do not get. Now, what's nice is with the Freedom of Information Act, you can actually download her lawsuit where she spells words like tuition incorrectly and has discovered a new type of discrimination previously unknown on this planet: academic discrimination. The school did more for students with higher GPAs than lower GPAs. Yeah. So I can't promise a job, but we have a lot of Williams alums who are working in industries related to sports analytics. And so if you have a lot of basic skills, there's a tremendous amount of things that you can do. A lot of it is something that you have, that a student who goes to maybe an hour school might not have. Is you might actually have better social skills, you might have better presentation skills, you might be more well-rounded. At some point, there's a lot of talented people. Who here has heard the phrase, you're 1 in a million? Who knows the rest of the phrase? Which means there's 1,000 like you in China or India. It's not enough to be smart. Everyone's smart. You have to be noticed. We have the oldest alumni network in the country. This is something to take advantage of. And so I'll be trying to get some of the alums involved in this class to varying levels. You need to be able to present comfortably. You need to be able to convince people to do what you are advising. And so I've got to be careful about which stories I say when things are being recorded. So I'll save that one for a technical malfunction later. But it is often very hard to speak in front of people. When I was an undergrad, I was an extreme introvert, same in high school. When I was in grad school, one of my friends said I should run for social chair. I go, you really want somebody who likes being with people to be a social chair. I don't think you really want, math geek who just wants to do math. But she pushed me, and that night at dinner, I said, okay, if one of my friends will run with me, I'll do it. There's 3 positions. And one of my friends stood up, and it was one of the best things I could do. So there's going to be a lot of presentations from you throughout the semester. So I want you to be doing that rather than taking exams. If you really want to do long technical exams, we can do that. It's not nearly as much fun. Much better for you to find papers that you are interested in. What should we talk about in March? March Madness, right? I mean, it's mandatory in a class like this that we have to talk about March Madness in March. But when should we start talking about it? Yeah, right. But before it starts, it's really easy to talk about predictions after the tourney is over, right? Before it happens, I had a colloquium student last semester who gave a talk on a method to predict long shots and to bet intelligently. And I'll be careful because this is being recorded. If I had been the referee assigned to the paper, I would have been a little bit concerned over the fact that they used the entire data set to come up with the values of their parameters and then saw how well they did on the data set that they used to get their parameters. What you often like to do is split your data into, say, even year, odd years, and say, yeah, they're probably about the same. And you train the data on one and then see how well does it do on another. If you've put in these upsets, and if you actually look at how well it did very well. I would invest in that company. But then if you look at how well it did in the years afterwards, did not do that well. And so trying to figure out what is a good way to model something like March Madness to try to predict who's going to win. Up until a few years ago, you could say no number 1 seed is going to lose in the first round. It's only happened once, or has it happened twice? Once, okay. Still think it's just once. You're pretty safe with no number 1 seed is going to lose in the first round. But how do you start figuring out which are the games that are likely to be upset? All right, another sport that I love is college football. College football is ideally designed for mathematicians. And the reason is you don't have a lot of head-to-head games between the teams that are competing for the national title. I went to the Ohio State University for a year as a postdoc. And Ohio State is one of the few schools that actually has a legitimate football program where they would actually reach out to other contenders and say, let's do a one-on-one. We'll play 1 year on your field, you play 1 year on our field. And this was before the playoffs for football. And basically, if you lost that game, you basically destroyed your chance at a national title. But if you won, you punched your ticket and you are now on the short list. And so it's a high-risk game. Most teams now, you have your conference schedule, you have a couple of games outside your conference just to make sure you're bowl eligible, but you have very few good games between the conferences. So how do you judge how good a Big Ten team is? Out of curiosity, how many people know how many teams are in the Big Ten conference? 14. 14 as of today. And what will it go up to? 16. It'll go up to 16. So how do you judge how good a Big Ten team is versus an SEC team that plays in these wonderful tropical paradises with beautiful, I'm sorry, that's editorializing, that plays, a very different schedule? Well, when we have bowl games at the end of the season, you can try to see how well they're doing, but during the season, you don't have a lot of direct comparisons. You do occasionally have a few games between different conferences or between common opponents and whatnot. And so there's a lot of great mathematics done about how do you rank teams when you don't have direct comparisons. Are there any fans of, in Europe, they say football, we would call it soccer, Premier League and stuff like that. And so they have an interesting system where basically everybody plays everybody. And I saw an interesting proposal that they should redo the NFL and they should have 2 levels of the NFL. Put half the teams in each, and the top 2 teams in the first half play each other for the Super Bowl. And everybody plays everybody. So that you're not going to have a home and away game against everybody, but you have 1 game against everybody. So everybody plays everybody. It's a balanced schedule. And then you have the other league, lesser NFL, where everybody plays everybody. And at the end of the year, similar to the European soccer leagues, you take the 2 or 3 worst teams in the top NFL and you move them down to the lower one. And you take the 2 or 3 best teams in the lower and you move it up. And that way you have a much better comparison situation. What interesting fact, and again, I apologize, but this is a math and sports class. There will be some sports questions related to what's going on. If you don't know any of it, it's not going to affect any of your grades. Does anybody know what might be a little bit annoying to some purists about the playoffs in the NFL this year that might bother some people? Yeah.
You have like the Bucks were 8 and 9. They just the playoff game.
Yes.
Just the Lions were 9 and 8. Just the playoffs.
Yes. And so a situation like that where a team that's under 500 is not only in the playoffs, but hosting. A couple of years ago, the Seattle Seahawks under Pete Carroll went 7 and 9. And they hosted, I think it was New Orleans. And, they beat New Orleans at home. But, people like a 7 and 9 team. A huge part of this class is to try to find what's a good metric. So if I give you 7 and 9, what do you think? Good team, bad team? Bad team, well, you could be generous and you could say an average team. So here's one of my statistics. When you're looking to see how strong a division is, because in football you play your 2 games against each team in your division, mod out, throw away all the intra-division games. Because if I have 2 teams playing in my division, either they both tie in the game or one wins, one loses, the net effect is a tie, the net effect is 500. So when you look at the outcomes for all these intra-division games, they're going to be 500. So for the Seahawks to be 7 and 9, considering that 6 of their 16 games were against teams in their division, and their division is below 500, if you throw away those intra-division games, you see just how bad that division was. The Red Sox did not have a good season. And, the prognosis for next year is, more of the same. But they were in a tough division. And, the American League East sent, 3 teams to the playoffs. They are changing baseball for next year where you're not going to have as many games against your division. And there's a lot of interesting stuff going on here. So the reason I'm bringing this up is this is the main theme of the course, is trying to find what is the right metric for what we want to study. At the end of the day, it's about winning, either winning your division, winning playoff games, winning the championship. And if I tell you a team is 7 and 9, that gives you a good amount of information. But it's not the full story. 7 and 9 in what division and what time period? And if you're 7 and 9 in a division where the other 3 teams are making the playoffs, the Patriots missed the playoffs this year, but they were in a stronger division. It's not as bad as a 8 and 9 in another division. So you really want to put things in perspective. You really want to find what is the right metric that really gets at the heart of what you're trying to study. And for different sports, what the right metric is evolves greatly over time. And so we'll be trying to figure out what is the right metric to study. Last piece of advice is learn how to manage your time. No one else is going to do this for you. It is extremely important to make sure that you are doing things on time, getting things done. For a class like this is going to be a more casual 300 level class, but there will be presentations where this is your chance to show how can you come up with some convincing arguments. Okay, so what I want to do is talk a little bit about some professional sports, just to put things in perspective as to how much we're talking about. So I just did a quick search online. What is the revenue by league? And you see football coming in at 13 billion. And then you have baseball 9.5 billion, your Premier League for soccer, your 5.3 billion, and so on and so on and so on. Just to get a sense of the magnitude and how much things are. Biggest difference between football and baseball is the number of games. About 10 times more games in a baseball season than in a football season. And that has tremendous implications for how much an individual game is watched. So when you're trying to figure out, say, value of commercials and whatnot, there's a lot more people watching each individual game in football, I think. All right. One of the big things I want you to get out is whenever you see maps, to try to draw as much as you can. So I gave this question in my 150 class earlier today. Can anybody tell me what this is a map of? Yes.
This was who people were, the state was rooting for in the Super Bowl. Was this 51?
I believe it was 51. Who are the teams? 53. Okay, 53. It was
51.
52 is the Eagles.
52 is the Eagles.
Yeah.
Okay. So what do you notice when you look at this? And first of all, I will say this is a continental map, or lower 40. I say lower 40 because Alaska is continental. So who are the teams playing? Rams and the Patriots. Years ago, when the Carolina Panthers were in the Super Bowl, I heard perhaps the most absurd comment ever from football commentators. They were talking about how Carolina is unique among all professional sports franchises in North America. They are the only franchise not named after a city or a state, but after a region. Does anybody know who Carolina played in their first Super Bowl? The New England Patriots. And they're going on and on and on about the name. Now, first of all, who cares what the name is? But second is, do you realize they're playing the New England Patriots? When you look at this map, what immediately comes to mind?
So that I think that one little region in St. Louis.
Yes, this very good. This is St. Louis. So you notice that a lot of people miss that. Why is St. Louis rooting for the Patriots?
It's the Rams moved from St. Louis.
Right, the Rams moved from St. Louis. So they might not actually be rooting for the Patriots. They might be rooting against the Rams. What else? Who else is rooting for the Patriots? Yes. Louisiana.
Rooting against the Rams.
Yes. So this was the year where there was a pass interference call that was just horribly missed at the end of the game between the New Orleans Saints and the Rams. And it was so bad that after the game, the officials, the NFL actually apologized and said, wow, we really missed that call. And it would have given essentially the game to the Saints. They would have been able to run out the clock and have a chip shot for a field goal. And in fact, I'm going to New Orleans later today to meet up with a colleague. He is part of a Pulitzer Prize winning team. And he told me that they were so pissed after this play. I mean, he sent me the newspapers and it was just wonderful to read the newspapers. But when the Super Bowl actually came around, a lot of the bars did not broadcast the Super Bowl. They just replayed an old Saints Super Bowl. They were just on such a strike against the NFL because it was just such a blatant pass interference that was just missed. And the defender did what you coach. Look, if he catches the ball, the game is over. I might as well and hope for the best. And it worked. So whenever you see information, first, if you're preparing the graph or the plot, you want to figure out what do I want to show? And the second is when you see it, what story can I grab from this? One is, I did a little search today for sunrise and sunset times on the East Coast. And so we have Providence, Orlando, and DC. And what do you notice when you look at this plot? Discontinuities. So this is strange. I mean, for the most part, it looks like sunrise and sunset is continuous. It's seasonal, okay. And then you have these 2 days where does something happen to the Earth's orbit? So what's going on? Daylight savings. And so again, when you see plots, focus on the places where something interesting is happening. There's usually a story going on there. Sometimes it's very easy to see. If you don't see this, I don't think you have the prerequisites for the course. You should be able to see, oh, something's happening here. This one over here, you're noticing this little dot. It's a little bit harder. You should still be able to see the dot, but the discontinuity here is very clear. So you want to be thinking about how you're presenting information. What story are you telling? Okay. So we're going to talk about a lot of methods and a lot of statistics. Here's one of my favorites. This is the log5 method from Bill James. So assume A wins P% of their games and TB wins Q% of their games. Which formula do you think does a good job of predicting the probability that team A beats team B? And so what I'm going to do is I'm going to just pause this for about 2 minutes. Zoom. All right. So any thoughts? Yes. Yes.
I feel like it has to be one of the bottom two.
Okay,
The numerators, if you take out P, you get P times 1 minus Q, which is the probability that team A wins, and then times the probability that team B loses.
okay.
Yeah, I was thinking the bottom right corner, because I think you subtract out the -2PQ because it's mutually exclusive. If you can have both A and B win.
Okay,
Also, another way I think to make the argument is to test out the case where P and Q are both 1/2.
okay, good. So this is looking at special cases. So if P equals 1/2 and Q equals 1/2, what should be the probability that A beats B? Half. Actually, let's generalize a little bit. Let's say A wins P% of the time and B wins P% of the time. What should be the probability that A beats B in that case? 1/2. So if they're basically equally good teams, so if P equals Q, it should reduce to 1/2. So let's take P equals Q. Which of these is going to reduce to 1/2? So you can start doing some tests like this. I'm not going to do algebra in class. No one wants to see a professor do algebra in class. But that's a test you could do. What happens in the special case? I have an idea. Can you give me another case where you know what will happen? Yes.
Adds if Q is 0 or P is 0.
Good. I was about to say the Detroit Lions from a couple of years ago, where they went over an entire calendar year without a victory. So imagine you have a team that never wins. What should happen? So if Q equals 0, it should reduce to 100%, right? And so if Q equals 0, the first definitely reduces to 100%, so does the second, so does the third, so does the fourth. So that doesn't help us. What if P is 100% and Q is less than 100%? What should happen?
100% A wins.
Right, so do we think that it should be 100% in that case? What if you have 200% teams playing each other? I would almost say that it should blow up and somehow in the limit it should converge to 50%. So maybe take the limit as P and Q go to, maybe P equals Q goes to 1 or something like that. Years ago, I think the game was called Hardball. They might have shown a clip of it or a later version of it in the movie The Princess Bride when the kid is sick in the beginning. My brother and one of his friends created players, and my brother created the ultimate hitter who got a home run every single at bat. And his friend completed the story by creating the ultimate pitcher who struck everyone out. And they met each other. And the computer just hung up trying to figure out what the hell do I do? And it came up with the only solution that makes sense in the end. So what do you think happens to the guy who always gets a home run faces the pitcher who always strikes everyone out? How do you compromise?
Wow.
Nope, but close.
Yeah, pitch.
Nope,
Game crashes.
nope. Did not crash. It was very good coding that it put in something to stop the crash. I actually crashed a psychology experiment as a guinea pig in college, but I'm happy to talk about that at some point. So a walk would be, yes?
Maybe intentional walk?
Nope, nope. So what happens with a walk? Where do you end up? Okay,
That would double.
a double. So it said, well, you know what? A home run is 4 bases. A strikeout is no bases. I'll give you a double. It was really good coding that it forced it to come up with some outcome in that. There's other cases we can look at. Can anybody think of another case we could look at where we should have some idea of what the answer should be? So some special cases of PQ. I'm huge on special cases to see is something reasonable. So let's imagine Q equals 1/2. So Q is an average team. What do you think might happen if your P is greater than 1/2? Let's say your P is 80% and you play an average team. How often should you win? Maybe 80%. maybe in the special case when Q equals a half, then your probability of winning should just be P because you're playing an average team. What if Q is less than a half and P is greater than a half? What should be the probability of A winning?
I'm greater than P.
It should be greater than P. So, we're starting to get lots of special cases. And so I just wrote down a few. If P equals Q, the probability A beats B is 50%. If P equals 1 and Q is not 0, 1, A always wins. If P is greater than a half and Q is less than a half, then the probability should be greater than P. If Q is a half, the probability A wins is P. So when you do stuff like this, you can actually eliminate a lot of the possibilities. This is not a proof that one of them is true. So this is one of my caveats. So if you've seen this before, can somebody reduce 16 over 64? I want to check people's algebra. 1/4, thank you. 19 over 95. This is taking a long time. I mean, I know we just had a pandemic and people's math has suffered a little bit, but come on. 1/5, thank you. Let's try to get these a little faster, guys. 49, that's hard to read. 49 over 98. 1/2, 4 over 8 is 1/2. All right, one more, this is getting sad. 12 over 24. Sorry? 1/4. Do you want me to show my work? 16 over 64, cancel the 6s, it's 1/4. 19 over 95, cancel the 9s, it's 1/5. 49 over 98, cancel the 9s, it's 4/8. So clearly the way you divide two ratios of two-digit numbers is if the anti-diagonals are the same, you remove them. And so 12 over 24 is just 1/4. Just because you've provided evidence does not mean you have a proof. So if you look at a lot of the literature in sports, a lot of it is, I've noticed this pattern. And as a mathematician, I go, okay, that's step one. And now I'd like to come up with a model that gives me some confidence that this pattern will continue and that this is not just something that's happened a couple of times. Is there a reason why this is happening? Do we expect this to continue? Another way I could have done this part of the lecture is I could have actually kept one of these numbers in reserve so that if you disbelieve it, you can say, well, let's try another one at random. Let's try, I don't know, 19 over 95. And you just keep something in reserve. It is very easy to try to mislead people based on how you present information. And so if something is wrong and I choose a couple of cases where it seems to work, I can easily influence you. Before I forget, cell phone policy for the class is either if someone's cell phone goes off, everybody has a quiz the next day, or if someone's cell phone goes off, they provide snacks for everybody the next day. You are welcome to try to call my cell phone or have one of your friends try to call my cell phone during class. If you are on a short list to get a Medal of Honor from the president and are expecting a call during class, by all means, let me know. Or if you have a job interview and you're waiting to hear from something, by all means, don't put your phone on vibrate or silent for something like that. Absolutely make sure that you can hear that call, but otherwise, have the phone off. Okay. So here's a sketch of the proof. And again, I'm trying to come up with a semi-reasonable model. Let's say that the probability that team A has a good day is P, and the probability it has a bad day is 1 minus P. And similarly, the probability that B has a good day is Q, and that it has a bad day is 1 minus Q. Then A will win if it has a good day and B has a bad day, and B will win if B has a good day and A has a bad day. So we form like a little tree diagram. And so with probability P, A has a good day. With probability Q, B would have a good day as well. Well, in that case, we would have to just play again. They both had a good day. Let's run it again, and we'll keep running until one has a good day and one has a bad day. And then the probability that A wins is going to just be P times 1 minus Q. And then the probability that A loses would be 1 minus P times Q. And so if I want to figure out what is the probability that A wins, I look at just the outcomes that matter. These ones, I just feed the probability back to the top and I run it again. So if you imagine I have 1,000 games and I see what fraction end up in here, and then I look at the number that ended up here divided by the total number in just those two boxes. And that would get me P times 1 minus Q over P1 minus Q plus 1 minus P times Q. And this was the P1 minus Q that had been noted, that the numerator factors, and you can interpret it as P times 1 minus Q. So later in the semester, I will bring in some Rubik's Cubes to just illustrate how you can try to fool people by how you present things. And so I'll actually skip a little bit ahead to do one of my following. You won 3 of last 4 games. So if I tell you your team has won 3 of the last 4 games, is the team playing well? What's the winning percentage?
Well, if you won 3 of your last 4, you lost the one before, so you won 3 of your last 5.
Not necessarily, but if you have a human being and not a mathematician, right? If you had won 5 games ago, you would have said, I've won 4 out of 5. So 1, 2, 3, 4, 5. We know there has to be a loss here. What happened 4 games ago? Why was there a win?
That started the last 4 games. If there wasn't a loss, you would have just said you won the last 3 games in a row.
So we know we have a win here. What about the first 3 games? What must be true in the first 3 games? Good, so 2 wins, 1 loss. So in the last 3, you're 2/3. In the last 5, you're 3/5. So this is about 66%. This is about 80%. I'm sorry, not 80%, 60%. And I'm sure somebody will yell at me, it's closer to 67%, 60%. But if I look at the last 4, you have 3/4, which is 75%. So by presenting the information in just the right way, I can make the team look a lot better than it is. This is something we really want to be careful about. Especially if you ever become, say, a manager and you're negotiating with an agent of a player as to what statistics are they going to be presenting you. Do these statistics matter? The biggest theme for this class is trying to figure out what statistics matter. So the other class I'm teaching this semester is multivariable calculus, Math 150. I have easily known calculus longer than any of the students have been alive. Calculus is taught very differently now, or at least it should be taught very differently now than when I was a kid. What's the biggest change in calculus? We don't have a new definition of the derivative yet. That's been pretty stable for a long time. But what's the biggest change in how you do calculus now? Any thoughts? If I give you an integral to do, how will you do it?
We use technology.
You use technology. I was trained in how to use lookup tables. How do you convert the integral to something that you can recognize from the table of integrals you have on you? One of my physics professors in college said, you need to have 2 tables of integrals, a big monster that you keep in your dorm room and a smaller portable one to have on you at all times. It's the 21st century. We don't do that anymore. We have technology, use it, right? So we're not going to be doing a lot of the standard calculations anymore. The computer does that. We have to figure out what calculations do we want it to do. And that's why for class like this, I'm not going to be overwhelming you with material. The real purpose of this class is to think like a mathematician, is to figure out what things really matter. What do we want to focus on? What do we want to investigate? It's finding what's the right statistic, what's the right metric. Trying to get as much information as you can out of everything that's going on. And again, at the end of the day, it's not enough to just know what information. You have to be able to convince people. And that's where you actually have a competitive advantage over students from other schools. This is a small liberal arts college. You have the ability to talk to people, hopefully intelligently, on a variety of topics. I will share some stories when we have some technological malfunctions about just interview processes and whatnot, and just how to do stuff like that. All right, so going back a little bit. So can someone define the mean for me? So mathematically, yes,
The average.
the average. Now I'm actually pushing you a little bit in a different direction by saying the mean. So some of you know, and I actually mentioned earlier today, where one of my postdocs was. What school was it? Nope. The Ohio State University. Now, most of the time in mathematics, we don't have these. We have a. This is a proof of Pythagoras. There's many proofs. Even a US president is credited with a proof of Pythagoras. Williams grad. Garfield is credited with a proof of Pythagoras. Different proofs illustrate and illuminate different aspects of the problem. So when I say the mean, that's almost implying that there's only one mean that you could look at. And the reason I want to do this is talk about different types of statistics. So everybody has seen the arithmetic mean, the average between two numbers, x plus y over 2. And we'll assume x and y are positive numbers. So can somebody tell me a property the mean should have? What should the mean of two numbers x and y have? What kind of property? What should be true about the mean?
Should be in between.
It should be in between. And and can you give me a special case for x and y where you know what the mean will be?
If they're equal, it will be.
Good. So when I'm trying to find the mean, whatever statistic I come up with, I want the mean of x and y to be somewhere between x and y, probably strictly between if they're different, and exactly x if they're the same. And so, the arithmetic mean satisfies these properties. And so it's not that hard to just go through and show. I'm not going to go through the proof. It's pretty straightforward. And so I'll write AMXY to denote the arithmetic mean. And the question is, are there other types of means we could look at? And so we want your two properties. It should be between x and y. And without loss of generality, let's assume x is smaller than y. And then the mean of x and x should be x. So if you already know what the answer is, you can't guess. But if you haven't seen this before, can anybody give me another function that will satisfy these properties? Yes. Good. So one thing is you could put different weights. And this is what you see in a lot of classes where midterm is 40%, finals 45%, homework 15%. You can put different weights like that. Or maybe you just have midterm and final. The midterm is 30%, final is 70%. And if I do something like that, I'll get something between. So that's one possibility. Another possibility is what's called the geometric mean. So it'll be the square root of the product. And so just doing, it's always nice to do specific cases. Let's do 2 and 8 or 1 and 100. And you'll see that in these cases, it does live between. Is that always going to be the case? Or is this something like the 16 over 64 that in this particular case, it was between, but maybe it's not always between. So can we quickly prove this? Well, it's not too bad to show. We know x is less than or equal to y. So x times x is going to be less than x times y is going to be less than y times y. So when you take square roots, you'll get x is less than or equal to the square root of xy is less than or equal to y. So it is going to be between. And then, of course, just doing the special case when they're the same comes out immediately. So this is a good notion of mean. We can now talk about, we have two different choices of the mean. Which one is right? Which one is better? Well, it depends on the problem. And so if we take the numbers 2 and 8, the arithmetic mean is going to be 5. The geometric mean is going to be 4. These numbers, of course, are cooked up so that I get nice integers. This is actually part of a talk that I gave to younger kids during the pandemic. Which do you think is a better mean? I'll give you 2 and 8, 5, which is the halfway point, or 4, which is closer to 2. I mean, 5 and 4 are not horribly different. Let's do a more extreme case. Let's do 1 and 100. What would the arithmetic mean of 1 and 100 be? Arithmetic mean is 50.5, and the geometric mean 10. So you can see, if you got a 1 on the first test, but then really studied and got a perfect score 100 on the second, with the arithmetic mean, you move up to a little bit above 50%, and the geometric mean, you're almost indistinguishable from 0. So the larger value gets a much smaller weight in the geometric mean. And so it turns out that you can prove that there's actually a relationship between them. So in this case, I calculated that the arithmetic mean is 7.5, the geometric mean is 6. The previous case, it was 5 for the arithmetic, 4 for the geometric. We have 2 data points. Anybody want to make a conjecture of the arithmetic versus the geometric? Oh, no, 3 data points because we did the 1 in 100. Anybody want to conjecture a relationship between the arithmetic and geometric mean? You got 3 data points.
Arithmetic mean will be larger.
Yes. How confident are you?
Means it's super confident.
Yeah, especially when I'm giving the numbers, right? So I went to Lanesborough Elementary to do math with 4th graders, and I said, I can't lie, but I can mislead. I was impressed with how many of them knew what a hustle was. So, it does look like there is a relationship between the two, and it looks like the geometric mean is always less equal to the arithmetic mean. There's lots of different ways of proving that. And again, I will always have the slides posted. One simple way is to use, FOIL, and this was just a chance to talk to younger kids about, why might we care about some of the stuff you're learning in algebra? And if you just go through the algebra and expand things out, one of the most important inequalities in mathematics is if you square a real number, it's greater than or equal to 0. So if you just square the square root of x plus the square root of y, and you just go through and do all the algebra, at the end of the day, you'll get the geometric mean is less than or equal to the arithmetic mean. So I strongly encourage you to just go through and just do the algebra if you haven't seen it before. There's lots of different proofs if you're interested. I'm happy to share some other ones. But now let's try to generalize. What if we had 3 objects? What if we have x, y, and z? And of course, how could y be smaller than x? And how could z be smaller than y? So we'll assume 0 less than or equal to x, 0 less than x less than or equal to y less than or equal to z. The arithmetic mean would be the sum of 3. The geometric mean would be maybe to the 1/3 power. And you can prove that these will be means, and they'll satisfy all the properties you want. But I could look at other symmetric combinations. I could look at all products of 2. I could have x times y times z, x plus z. So let's add them up, maybe divide by something, because the arithmetic likes to divide, and maybe I raise it to a power because the geometric likes to multiply. So I'm going to try to balance the 2. So we're going to discover a new mean right now. So can anybody think of any cases to investigate where we might be able to figure out what some of these exponents are? Well, the bottom does the case when x equals y equals z. If we do x equals y equals z, then we're going to get 3x squared over a to the b power equals x for all x. So any thoughts on what we should have for the exponent? Any thoughts on a? Any thoughts on b? Yes.
Make a 3 and b.
Yeah, if you make a be 3, that'll cancel the 3s. If you make b 1/2, that's going to cancel that. And so that's an extremely reasonable guess. And so if we calculate the triple mean, we get 47/3 to the 1/2. I'm sorry, it's not exactly an integer, but I got it close to 4. So it is more than 3, it's less than 5. And you can compare this to the geometric mean and the arithmetic mean. So we know that the arithmetic mean is greater than the geometric mean. Where do you think this one might sit? So you've got the arithmetic mean is the largest, you've got the geometric mean is the smallest. Where might you put this one? Yeah, probably in between. And then if I started to have 4 things, then I could do maybe x plus y plus z plus w plus y. So looking at all these different combinations, and you can ask, how do they all sit? And so there's a beautiful paper by some of my colleagues looking at some of these. As a final thought about this, how many of you ever heard why we care about logarithms? So you actually had a teacher who in high school who told you or college?
It was college.
Okay. Yeah. So basically, a lot of times the way math is done in high school and middle school is Moses comes down from Mount Sinai and, thou shalt do the following. And there's no justification of why we care. Logarithms allow us to compare items that span many orders of magnitude. They also allow us to linearize relationships that are not linear. How many of you have done regression? So if you've done regression, if you take a logarithm, you can often make nonlinear relationships linear, and now we can use method of least squares. And so if I take logarithms, well, the log of a product is the sum of the logs. Really, the geometric mean is related to the arithmetic mean through taking the logs of the inputs. Okay, so the last thing, and I will be sending you an email about this, is I want you to order these cards, and I'll send you details about this, from the most expensive to the least expensive. And then we need to figure out what statistics should we use to judge how well you've done. All right, so I'll send details about this. But this is the whole theme of the class, is trying to come up with the right metric. How should I score how good of a job you're doing? And I'll send you details on this. All right, so this is a good place to stop.